Hello everyone, we are now in Module 4B and this is the numerical solutions to ordinary differential equations. Basically, we'll be discussing the Euler method, midpoint method, and the Runge-Kutta method. Okay, let's start. In your CE24, we already defined ordinary differential equation as an equation which contains one or several derivatives of an unknown function. Okay, yung unknown function na yun, it's in terms of an independent variable x or sometimes time t. Okay, and ODEs or ordinary differential equations are uh, containing ordinary derivatives of a single independent variable. So dapat single or mag-isa lang yung independent variable natin sa equation. These are some examples. First derivative is equal to cosine x. We have a derivative term and a term containing an independent variable x. We also have y prime, y double prime plus 9y equals cosine x. Again, we have a single independent variable term. And then second derivative and another term which is the unknown function itself. And some extension na, ganun pa rin naman yan. We have a term with derivatives, tapos the function itself, and the independent variable. Okay, as you can see, isa lang naman yung independent variable dito. So this is an ordinary differential equation. And from CE24, we are solving these differential equations. Ano yung kinukuha natin to get the solution or ano yung solution sa differential equations? Okay, ito yung kailangan ma-satisfy. Okay, ang solution sa differential equation is a function. Okay, this function should not contain any derivative. So dapat walang derivative doon, and it has and your dependent variable has a functional dependence on the independent variable. Okay, so you can express yung dependent variable natin explicitly in terms of the uh, independent variable x. Okay, and of course, if you substitute yung function solution mo into your ordinary differential equation, dapat ma-reduce into an identity yung equation na yun. Okay? So that's what we learned from CE24 and how yung methods natin on how to analytically solve for the solution of to solve the solution to differential equations. We have these. Okay? We know that the method to be used is dependent on the ODE type. Okay? So kapag folde, ito yung ginagamit. Okay? Pag homogeneous higher order ODEs with constant coefficients, meron tayong characteristic equation. Non-homogeneous na higher order ODEs naman, gumagamit ng MUC or MVP, eigenvalue problem pag systems, and some others kapag nonlinear ODEs. Okay, and from all of these methods, analytical methods, ang sinasolve natin is a solution function. Okay, so f of x or f of y yung sinasolve natin. So function. Okay? But this time, sa numerical methods, ang isa-solve natin na solution to ODEs are points. Okay? So when we solve for the solution to ordinary differential equations, numerically, ang ginagawa natin is kinukuha natin yung approximate points, okay? Approximate values which are close to your analytical function solution. Okay? And yung numerical method, applicable siya. Okay, marami siyang applications kapag yung problem natin are nonlinear equations. Okay, involve nonlinear equations tapos mahirap pakunan ng solution analytically yung mga pinakita nating methods earlier sa previous slide. So, anong ginagawa sa numerical solution or sa numerical methods? We are discretizing the problem, meaning okay, kinukuha natin yung approximate value ng dependent variable y using a discrete set, okay, of values of independent variables. So, at certain independent variables x or t, sinosolve natin yung approximate value ng function solution natin. Okay, so discrete number of points yung kinukuha natin pag numerical solution. Okay, and these points are close. Okay, kapag kinraf mo yung points na yun, it's close, they are close to the analytical function solution. Okay, again, so instead of a function solution sa numerical method, ang kinukuha natin is point, okay, or points, which approximates your function solution. All right, so let's start with the methods that are used, or the numerical methods for the first order ODEs. So, pag sinabing first order ODEs, this involves your first derivative muna. Okay? And for this content, Euler method and midpoint method muna tayo. But before that, let's introduce one type of uh, problem na ina-encounter natin kapag nagsosolve tayo ng ODEs. That would be initial value problem. Okay? Ang ginagawa rito is we're approximating a particular solution using numerical methods. Okay, again, kung maalala nyo, ang initial value problem or IVP, okay, ang given sa atin is yung ODE itself na isa-solve. Okay, and in addition to that, we also have an initial condition, meaning you have a single point, okay, or a single condition in which we know both the x and the y coordinates. Okay, so we know a single point, which is an element of your analytical solution. However, hindi nga natin masasolve yung analytical function solution talaga natin. So, gamitin natin yung derivative function. What is this derivative function? It's basically your function for your derivative, for your first derivative, di ba? Okay, basically iniwan mo or hiniwalay mo lang yung y prime na term on the left hand side, tapos the rest of other terms are napagsama-sama or naiwan sa right hand side, and this is in terms of x and y. Okay, so yung function na yun, if you substitute points there, you're finding the value of the slope at that point. Okay, so slope siya kasi di ba yun yung isang manifestation or isang what do you call this, interpretation sa first derivative of a function. So yung slope natin, it can be solved using this derivative function. Okay, and this IVP or initial value problem are applicable sa maraming engineering problems. And from your CE24, purgang-purga kayo sa mixing tank problems kasi yung analytical solutions natin, usually sinosolve natin siya sa mga sample mixing tank problem. Okay, so now that we know the concept of the initial value problem, let's discuss the first numerical method called the Euler method. Euler method, it's a first order method that uses tangent lines. Okay, bakit? Kasi nga meron tayong derivative function which is basically your slope of the tangent line. Slope of the tangent line at a given point in your function. Tama? So if this is your slope, meaning if you substitute points into your derivative function, yung makuha mong value is the slope of the tangent line at that point. Okay? So, looking at this graph, ito yung function solution natin na hindi natin alam and na-solve lang using analytical methods. Kapag numerical methods, ang nangyayari is if you are given a derivative function and they call this initial value or initial point. So, initial point yan, get the slope at that point, okay? Get the tangent at that point, tapos yung slope, ito, okay? Yun yung tangent niya at that point. And solve natin yung slope na yan if we substitute x naught and y naught sa function derivative or derivative function natin. Okay? And we can find this next point. Paano? Okay, since we're discretizing a set of points, constant yung distance between two points. So let's say that's h. Okay? So the distance between two discrete points ng set of points natin na gagamitin, that's always h. Okay? And if you recall, di ba, ang slope, okay, yung first derivative natin is the change in y or rise over run. Okay? So basically, yung delta x natin, that's h na agad. Okay, ito yun. And yung delta y is yung pag-akyat niya from your initial y value to your final or to your next y value. Okay, so if I multiply yung slope natin to your h, okay, so slope times h, okay, ang mangyayari, makuha natin yung delta y, di ba? So if I multiply the slope, yung f, ay yung makuha nating slope dito, if I multiply that with your h, you get this distance. Okay, and that's to be added to y sub 0 to get y sub 1. Basically, ito yun. Yung y sub 1 or yung next value of your, uh, the next y coordinate of your next point is basically the y coordinate of the previous point plus yung product nitong h tsaka yung slope ng tangent line at this previous point. Okay, gets naman? So, ito yung pinaka iteration na model na gagamitin natin for Euler method. Okay? Basically, kapag kukunin natin yung y coordinates natin, ito yung gagamitin nating equation. While pag kukunin natin yung x coordinates, basically, step size lang siya. Dagdag lang tayo ng dagdag ng h from your initial x value or t value until you get to their end t value or x value. Okay? So, again, yung y value natin sa next point is simply your y value from your previous point plus yung rise, which is the product of your slope, okay, o yung first derivative from your derivative function times yung step size h. Okay. Now, let's try applying this concept to an example. We're asked to apply the Euler method to the IVP using various step sizes just to show kung ano yung maging effect by using smaller step sizes. Let's start with 0.5 na step size. Okay, ito yung IVP problem natin or yung initial value problem natin. Y prime minus y equals 2x minus x squared. Where your initial value is the function solution value at x equals 0 is 1. Basically, yung initial point mo is 0, 1. Okay? We start with h equals 0.5. Sabi ko nga, when we say ang first natin kailangan mahanap is yung derivative function natin. Meaning, we're isolating y prime on one side and the other terms should be kept on the other side. So, y prime na to, iwan lang natin sa left side. Itong negative y, lipat natin sa kabila and then it will become positive y. So, y prime equals 2x minus x squared plus y or y plus 2x minus x squared. Ito na yung magiging derivative function mo. Okay? Meaning, if you substitute points here, makukuha na natin yung uh, slope, okay? Slope nung tangent line at that point. Basically, sa initial point natin, which is 0, 1. Okay? Since iteration to, it's very useful to create a table. Okay, we can compute na yung succeeding y values and of course, mas madali kunin yung succeeding x values kasi ano lang naman yan, add ka lang add ng step size dun sa initial x values mo. Okay, again, ito yung pinaka-Euler method natin for getting the succeeding y values. So, next y value is your initial y value plus h times the function derivative value at the initial or the previous point. Okay? So, ito siya. Using h equals 0.5, we start with the first iteration. Initial point is 0, 1. Okay, we substitute. Okay, di ba ito? Yung function na to, alam na natin na equal kay y plus 2x minus x squared. So, substitute niya lang na y plus 2x minus x squared. Okay? And dapat yung x and y coordinates dito are from your previous iteration. Okay? So, for the next iteration, yung x natin, basically, nag-add lang tayo ng 0.5. Okay? Sa example na to, ang gusto niya lang ipakita is from 0 to 1.5 na values ng x. Okay, so madali lang kunin yung x coordinates. Yeah. Kasi constant ang yung difference nila, yung step size. Okay, yung mga number of points na yan, basically, nakadepende naman sa problem. Hindi naman stated dito. Pero, siguro ang gusto natin kunan ng solution is the interval 0 to 1.5. Okay? Now, we know this initial points. We can substitute here para makuha natin yung next value ni y. So, how do we solve that? We simply substitute 0 and 1 kay x and y, x sub n and y sub n respectively. Okay? So, makuha mo y sub 1 or yung next value ni y mo is 1 plus 0.5 yung h times 1 plus 2 times 0 minus 0 squared. Tama? And you solve that, you get 1.5. Okay, ito yung okay, 1 plus 0.5 times 1 plus 2 times 0 minus 0 squared. Okay? Now, this is your second iteration. And your third iteration, ito naman yung substitute natin x and y dito. Okay, so as you can see here, 1.5 yung previous y value plus yung previous x value times yung function derivative natin. Derivative function natin, substituting yung x and y ng previous point. Kaya 1.5 plus 2 times 0.5 minus 0.5 squared. And you should get 2.625. Okay, repeat that to the next iteration, you get 4.43750. And when you graph these points, you get this. Okay, ang mga points na yan, hindi talaga siya points ng ano, except for the initial value. Yung mga points na yan, hindi talaga siya points sa actual or sa analytical function solution natin. Okay, so approximations ng itong mga points na to. Using yung mga tangents natin. Okay, now, what if we try using h equals 0.1? Meaning mas maliit na step size. Basically, ganun pa rin naman yun. Yung gagawin natin process sa pagkuha ng y. Kaya ang mag-iiba lang dito na value is syempre si h and itong mga coordinates ng x and y. Okay? So, we start with 0, 1. Okay, and then yung x values, just keep on adding 0.1 until you get to 1.5 kasi 0 to 1.5 yung gusto nating i-analyze. Okay? So, substitute natin yung x and y dito ulit to get to the next value of your y coordinate. Substitute mo si 0 dito, si y dito. Okay? And then you get a certain value. Okay? Sige, let's try ito. Saan to nang galing? We simply substituted yung y ng previous, which is 1.3879 plus h, which is 0.1 times 1.3879 pa rin plus 2 times 0.3 minus 0.3 squared. Tama? So what you get here is dapat 1.3879 plus 0.1 times 1.3879 plus 26 plus 0.6 minus 0.3 squared should get 1.5776, which is correct. Okay? So we simply substituted yung previous points dun sa solution sa equation natin to get the succeeding y values. Okay, yung mga x naman madali lang naman kunin. Okay, so repeat the process. You should get all these points, and upon graphing, you get these. Okay, and we repeat the process for h equals 0.02. Again, ang difference lang is yung values ni h and syempre yung points na sinasubstitute natin dito. Okay, you get these. Again, yung x values natin, just keep on adding yung what do you call this? Step size natin. Okay, until we get from 0 to 1.5. So 75 or 76 points in lahat. And if you graph yung points na yan, yung 76%, you get this. Okay, so compare natin lahat yan mamaya, yung nakuha natin na graph from different step sizes to the analytical solution. How do we get the analytical solution to this problem? C24 methods. Okay, so solving analytically, ito yung makuha mo dapat. na function solution. Diba? Again, pag analytical solution natin, ang nakukuha natin is a function. As you can see here, is a function of the independent variable x. Okay, and if we substitute, okay, yung, di ba, ang pinaka-counting points is yung h equals 0.5, apat lang. Sa x equals 0.5, 1, tsaka 1.5. So, try na lang natin i-compare yung function values sa points na yan, okay, or sa x values na yan at different step sizes. And yung analytical. Okay, ito yung nakuha natin sa h equals 0.5, 0.1, 0.02. And yung analytical, if upon substituting x equals 0, 0.5, 1, and 1.5 dito. Okay, solution function. You get these. Okay, and as you can see, sobrang lapit ng analytical kapag, or lumalapit yung solution, yung approximation natin from numerical methods if we use smaller step sizes. Bakit? Kasi lumiliit yung, for example, ito yung curve natin. So, kung sobrang liit lang nung ano natin, nung step size natin, sobrang liit lang din or maiksi lang din yung slope. Okay, so titigil lang dito yung second point. Sobrang lapit lang din sa original solution. Diba? Instead, comparing to kapag malaki yung step size natin, let's say hanggang dyan, ito yung slope sa first point. Ito yung second point. Diba? Ang laki ng layo nito dito. Pag sobrang laki pa nung step size mo compared dun sa pag malapit. Okay, tapos dyan, ganyan yung next, ganyan, so on and so forth. Sobrang laki nung discrepancy kapag malaki yung step size mo. Alright? And upon comparing yung graphs, ito yan. Diba? Ito yung h equals 0.5 compared dun sa analytical. Okay? Yung blue, pinakamalapit na, di ba? Sobrang dikit niya na dun sa analytical solution natin. Okay? So that's basically your Runge-Kutta method. Okay? Ano lang talaga siya. Formula lang for basically kapag x, kinukuha mo lang yung uh, step size, add ka lang ng add. And then for your y values, we use or we apply yung formula for the Euler method, which was derived from slope lang. Okay? Slope ng tangent lines. Okay? Now we get to the midpoint method. Okay, ito naman, same pa rin, na sinosolve is first order uh, derivative or ODE. Pero yung method niya or yung type of method niya is a second order method. Okay, you can uh, understand why upon explanation dito. Okay, this time instead na single slope lang nung tangent line, ang nangyayari is kinukuha niya muna yung midpoint between two steps, tapos doon niya kinukuha yung slope. Okay, so slope sa midpoint. So that way, parang mas malapit na siya, di ba? Instead na slope na sa first point, yung slope na lang sa second point, di ba? I mean sa midpoint. For example, ito yung first point mo. Pag ganyan, di ba ganito kalayo yung first and uh, yung uh, error between your approximated point and your real analytical solution, yung y curve. Comparing to the tawag dito, yung red, siya naman yung uh, midpoint method, di ba? Mas maliit yung naging error. Okay? This time, ano nangyayari? Kinukuha muna natin, ito yung pinaka-general form niya. Okay, yung derivation naman yung pwede nyo i-search na lang if you wanna know kung paano na-derive yan. But basically, ang unang ginagawa is itong term na to. Kinukuha muna yung y-coordinate dun sa midpoint. Okay? So, yung midpoint is yung x equals x sub n or yung previous x plus kalahati ng step size natin. Okay? And at that point, kinukuha, basically, ito yung ano natin change in x, di ba? Papunta sa midpoint. So, multiply natin siya sa slope of the tangent line from the initial point, which is still f of x sub n, y sub n. So, basically, parang ganyan siya. Okay, para makarating siya dyan. Okay? Pero, sasubstitute natin kasi yung point na yan or yung y value na yan together with, itong x talaga na to, itong point talaga na to. Sasubstitute pa natin siya further again dun kay function or kay derivative function natin. So, may approximate, dyan, slope, okay, and that would be used to get to the next point. Okay, multiply kay h, yung derivative or yung slope dyan to get to the next point. Medyo unclear lang. You can just actually read the derivation. Pero basically, we first get the point at the midpoint, okay, and then use that point to get to the next point. Okay, how do we do that? Basically, two-step predictor-corrector method yung gagawin natin. Okay, ito yung predictor. Basically, you're getting the point or yung y coordinate sa midpoint, di ba? Kaya n plus 1 half. Okay, sa gitna. So basically, yung previous y, dadagdagan mo lang siya ng product ng derivative or function derivative mo tsaka h over 2. Basically, slope times yung change in x. And then upon getting there, alam mo na yung point dun sa midpoint, yun yung isa-substitute natin dun sa corrector. Okay? Diba? X sub n plus h over 2 yung x coordinate sa midpoint, tapos itong predictor na y yung nanggaling dito. Okay? So, na-breakdown lang siya into two steps, predictor for the midpoint and then corrector for the next point talaga. Okay, let's try applying para mas maging clear. IVP by midpoint method naman. Same example, pero gamit lang natin is h equals 0.1 na step size. Okay, again, just like with the Euler method, we start with getting or isolating the y prime to get the derivative function. Still, that's still y prime equals y plus 2x minus x squared. And your initial value should be the point 0, 1. Okay? So, after that, kaya natin isolve yung predictor and corrector values. How? Ito yung formulas natin. Okay, for the predictor, basically, sinasolve lang natin yung point sa midpoint. Okay, yung approximate point sa midpoint. Okay, and then yung x value dun sa midpoint is simply your previous point plus kalahati ng step size natin. Okay, so yan yung magka-partner. On the other hand, yung corrector natin is, okay, using the predictor or yung previous approximate point from your midpoint, substitute mo yung point na yan dun sa derivative function. Okay, and then multiply by h to get to the next point na. Okay, ang kapartner naman yan is yung, syempre, previous point plus h na. Okay, kasi yan yung next point. Okay, so let's try tabulating. So meron tayong corrector and predictor. Okay, magsa-start tayo of course kay 0, 1, which is a point for the corrector. Okay, so initial values natin ng x sub 0 or y sub 0, corrector values sa mga yan. Okay, kasi endpoint yan eh. Hindi naman siya midpoint. Mga midpoint sila yung sa predictor. Okay, ang next natin kayang i-accomplish dito would be yung mga x values. Okay, kasi from corrector to predictor, nag-add ka lang lagi ng 0.5. I mean, kalahati ng step size mo. So, 0.5 ng 0.1. That's 0.05. So, add ka lang ng 0.05. So, that's your next x. Okay? And then, you can actually substitute yung point, yung previous point, yung corrector point natin to get the predictor point. Okay, so x na corrector tsaka y na corrector, substitute mo lang dito. Okay, so that's basically yung y sub n natin, which is 1 plus h over 2. So 0.1 over 2. You get 0.05 times ito pa rin, y plus 2x minus x squared. So that's 1 plus 0 minus 0, so 1. So you get 1.05 dapat. Okay, so tama. Okay, and then we use this predictor point to get to the next corrector point naman. Okay, syempre, yung next corrector x natin is simply dagdag ka lang ulit ng half, di ba? Kasi half from the half dun sa predictor, sa previous predictor, half ng step size. So, 0.05 plus 0.05, you get 0.1. Okay? And then we substitute this corrector or this predictor point dun sa corrector formula natin. Okay, so y sub n, that's 1.05 plus h, which is 0.1 times f of, okay, so substitute natin yung point na yan dito. Okay, so that's 1.05 plus 2 times 0.05 minus 0.05 squared. We should get, try natin, 1.05 plus 0.1 times 1.05 plus 2 times 0.05 minus 0.05 squared. 1.1 for, wait lang, 1.05 plus h, which is 0.1 times 1.05 plus 2 times 0.05 minus 0.05 squared. Wait lang, parang, sorry, hindi pala to 1.05. Y sub n pala to. So this should be 1.0 or 1. Okay? So with that, makuha mo dapat 1.1147. Okay? Tama. And then, predictor, yung x value natin, syempre, add ka lang ulit ng 0.05 dito. Kalahati ng step size natin. Okay, and then, gamitin mo ulit to dun sa formula natin kay predictor. Okay? And so on and so forth until you get to your endpoint. So, sa case na to, tumigil siya pagdating kay 0.45. Okay, pero pwedeng ituloy yan hanggang kay 1.5 like what we plan to do. Okay? So, paulit-ulit lang naman, corrector, predictor, corrector, predictor, corrector, predictor. And then you get these points. Okay, so upon comparing ito yung analytical values natin, by substituting yung mga points natin na to dun sa analytical solution na nakuha kanina dun sa previous example. Okay, and then yung Euler method na sagot, tapos yung midpoint method na sagot ngayon. Okay, and upon comparison, as you can see, sobrang dikit na or malapit na yung midpoint method na nakuha natin to the analytical. Di ba? Halos di na makita yung difference ng orange diamond dun sa triangle na maroon. Okay, basically, since second order approximation si midpoint, okay, di ba, may corrector ka, may predictor ka pa, so parang dalawang beses kang parang dalawang Euler method yung katumbas niya. Okay, so mas they call this mas powerful or mas lumiliit yung error when we're using the midpoint method compared to the first order na Euler method. Okay, so that's basically your Euler method and midpoint method. For the next content, I'll be discussing your Runge-Kutta methods. So for now, goodbye and thank you for listening.